The next speaker is Teddy Rendahl. He is a control engineer working at SLAC on LCLS. His major focus is on creating high-level applications and automation routines for LCLS beamlines. And he will present the Skywalker, a Python suite for automated photon alignment at LCLS. So Teddy, welcome.
Thanks for having me. As you said, I'm Teddy Rendahl. I'm going to be talking about Project Skywalker and Automated Alignment Suite at LCLS. I'm going to quick go through the motivation and goals of the project, a couple steps we had to take along the way, and finally our commissioning results and where we see ourselves going in the next couple months. Quick introduction to LCLS. We have 7 experimental hutches with 8 flat mirrors that deliver the beam between them. Each of these hutches is their own optics that actually focus the beam at the interaction point, whether it be KB mirrors or beryllium lenses. But it's up to these flat mirrors to reliably and accurately deliver the beam. The idea is the more accurate we can make the flat mirror system, the least that each of these individual hutches has to modify their optics at the start of every shift. It's made a little more complicated by the fact that it's common for experiments to run in serial. So that means that all of our hutches have to agree on a common axis of alignment, and things are only going to get more complicated in LCLS 2 when we add more mirrors, more end stations, but the good news is that there's a strong emphasis on automation from the start with that project. So I know a lot of you are probably curious about the name. I don't know if your facilities are anything like ours, but we kind of have an acronym problem. So we knew we didn't want to go with one of those, and when we imagined a terrified operator watching the beam walk across the screen as if guided by some mysterious force, Project Skywalker was born. So the main issue is that the pointing of the free electron laser is not repeatable enough for set and forget values, otherwise this wouldn't be a very exciting project. Largely because the source point is so far from some of our hutches, up to 400 or 500 meters, that even small differences in the pointing at the source can have huge effects downstream. So alignment needs to be done at the start of every shift. Also, there's about 190 devices in the common areas of the beamline, which can be an administrative nightmare for our operators. If an IOC goes down or if somebody leaves something in, it can be hard for them to identify what's actually affecting the beam they're seeing. So our ultimate goal is a single-click alignment system for the hard X-ray end stations. We decided to wait for the soft X-ray because they're being ripped out in 2018. So this system's just for the hard X-ray now. And the goal is that it should be done faster than the manual alignment, which on a good day can take about 10 minutes, but if there's issues, can take up to 45 minutes, especially in that mode where they're trying to agree on a common axis. There's actually 3 operators who all have to get on the phone with each other in that situation. There's the accelerator operator and then 2 beamline operators. And if you've ever played banana phone, you can imagine how troubleshooting in that situation can be very difficult. And the goal is full automation. So we don't want this thing to have to be babysat, and has to be reliable against drops in energy, clear beamline instructions, and be used 2 to 4 times a day. Just a quick glossary of the tools we're going to use. Flat mirror systems were new in May. The pitch mechanism is controlled by a combination of a stepper and piezo in series. The stepper does the coarse moves, while the piezo does the fine and also does some drift compensation over time. We have 4-jaw slits made by JJ X-ray that actually define the alignment. You can see on the image here to the right, you can see the shadow of the slits with the beam in the center. And what we're looking at there is one of these imagers or YAG screens, pop-in monitors. I'll use the terms kind of interchangeably. But it's a YAG crystal that fluoresces when X-rays are incident. Finally, we chose to use Python 3.5 and up, and we're using the OFID and Blue Sky packages developed at Brookhaven. A quick aside about Blue Sky. The main concept is that you abstract your scans into these experimental plans, and all these things are just a set of instructions. The plan actually doesn't execute anything, and then you feed it into the run engine, and that asynchronously handles delivering instructions to devices, gathering information, and packaging it up. So you can use it very conveniently for things like live data processing like you'll see today, or you can store it to disk. So before we can point the mirrors, we need to know where we're pointing to. At the start of the Skywalker run, you can either choose a new target, use a historical value, or you can remeasure using the slits. So what that entails is you have your unclipped elliptical beam here, you shrink the slits, and you essentially select the section that is aligned, take the centroid, and the difference between your two measurements are your error in pointing. So now for the fun part. We actually have to point a mirror to the target. When we set off with the project, we wanted this part to require as little prior knowledge as possible. The idea was that this makes it more robust in the end. If you build some big calibration table and then somebody comes in and just rotates your camera, all of a sudden you have to rerun everything. So we start the scan knowing nothing about the system. And I'm going to talk pretty generally about this part. In our case, we're assuming a linear model between the pitch and the encoder value, or the pitch and the centroid value, but really this could be any single variable function. So you can see on the scan I'm showing on the right, it's taking a two-shot average, so that's why you see this two-point clustering. We measure once, and then we take our naive step to explore the parameter space. And this, in this case, is actually the wrong direction from the target. But then with those 2 points, we know enough information to draw a line. Our first intelligent guess after the naive step gets us pretty close, and then with 3 data points, we know enough to almost exactly hit our target. So like I said, we need to define this common axis, and 1 point on 1 detector is not a line. So we need to do this twice, and we're actually going to align 2 mirrors at once to do this. First, we take the first mirror and the first detector and the second mirror and the second detector. And we're essentially going to use the brute force method to iterate back and forth, running this scan over and over again I showed in the last slide. And the idea is that this eventually converges on the solution, and we can increase the rate of convergence using some simple geometry. If L1 in this diagram is as small as possible, then the parasitic displacement you get by going back and forth is smaller because the second mirror affects your first detector measurement the least. And this is essentially what it looks like. You adjust one, go back to the other, but you've displaced the first measurement, so you have to iterate back and forth. That ends up looking a little like this. There's a few interesting things to notice in this scan. First, the very first time we align each detector, you can see that it takes multiple steps, but at that point our model's built, so every subsequent time after that, we hit the target almost exactly on our first try because we know exactly the mapping between the pitch and the centroid we're trying to measure. Here we're taking a 75-shot average, so that's why you kind of see these horizontal lines. And then finally, you can see how we converge pretty quickly. Each time we go back and forth between each mirror system, the other one's displaced a little less. So unfortunately, life is not as easy as a little 3-line simulation and some fancy matplotlib work. So we have to make heavy use of blue sky suspenders to stop the scan when the beam drops out. And we also have to make sure that strange shots from the free electron laser don't make it into our model. So we developed an in-house library that we're calling PSBeam. It uses OpenCV. It looks at things like if the eccentricity of the blob you're looking at changes drastically, you can throw a warning at the operator, or if we end up seeing 2 distinct separate centroids, you can throw a warning or something like that, or just filter the shot from the model more importantly. So in commissioning just the single mirror mode with no prior knowledge, with the beam completely off the detector, we're able to align within a pixel in 60 seconds. And the majority of that time is spent during the fine adjustment. So after we take that naive step and we only have 2 data points that can pretty reliably get us within 10 pixels, really most of the time is demanding such a fine alignment of 1 pixel. And at that point, we were using a Jupyter notebook, so there's a link there if you wanted to take a look. And then in the 2-mirror alignment, same idea. We're starting with no beam on the imagers, no prior knowledge about the system. We're able to align within 7 minutes. But that's not really the standard operating mode. If you seed it with the prior alignment values, you actually are aligning within 90 seconds. So keeping track of those 190 devices isn't too easy. So we developed a database that contains device positions and necessary metadata. And it has flexible backend support, so you can use MongoDB or just a JSON file if you want. And the idea is that this can inform our future automation projects as well by keeping track of the information we need to on different instruments. And we also developed a light path, which kind of takes EPEX devices and then reports their transmission. A device like a Photon stopper would be 0 or 100%, but certain devices are more complex, like attenuators and slits. And we need to let our operators know when they're in the beam. So we developed a PyDM user interface that's going into beta test next week. If you want to hear more about PyDM, my colleague Matt Gibbs is giving a Speaker's Corner presentation tomorrow at 5:45. You can see it here on the right. It's not exactly a work of art yet, but it gives some buttons for operators to press. We're also talking about creating a long-term storage for alignment results. We've always kind of entertained the idea of using a machine learning approach once we have enough information. So the first step in that is keeping an organized database. Also, our next alignment project is the hard X-ray split and delay system, which my colleague Abdul is going to be giving a poster presentation about at 4:45 tomorrow. And it's a little different. Instead of trying to hit a target, instead you're trying to maximize the signal on a diode using a rocking curve approach. We also want to fully separate the LCLS specific routines, and whether these go back into Blue Sky or whether they kind of remain a separate library remains to be seen, but the idea is that we want this thing to be easily portable to any automation effort, whether it's at SLAC or at another facility. Finally, for future improvements, we want to introduce some automated tuning. The idea is you'd use a quick diagnostic run to kind of inform the parameters that the operator might not have the time or care to go in and tweak. So for instance, you could imagine that you could intelligently select the average that you're going to take based on the beam jitter and things of that nature. It's also easy to imagine continued deployments to other pointing procedures around LCLS. And finally, these mirrors only pitch the beam horizontally. The pointing in the vertical still has to be done entirely at the undulators, so putting those into the system is on our to-do list. Some quick links. If you're interested in messing around with it, we have 2 different Conda channels, one for tag builds, one's for master. I also included OFID and Blue Sky links here. Documentation is up, and we're also pretty diligent about keeping up to date with our GitHub issues. We're not shy about putting what we're working on there. So if you're interested, take a look. Thank you.
Questions? No. I have one. As I understand, this is a preliminary alignment before an experiment. Mm-hmm. But do you plan to use it as a optimization between 2 experiments while the mirrors are already aligned by a first step, and to correct small minor deviations?
Yeah, I think that was actually. We were talking about including this kind of passive monitoring system where if once you align and then if things tend to drift, mm-hmm. you can either a warning will automatically be thrown or just the operator could go check to see if we're still in what we think is nominally aligned.
Mm-hmm. Other questions? How many people are working on the project?
How many?
Yeah.
I'd say it was like 3 to 4 FTEs over the last 4 or 5 months.
Okay.
Thanks.